Okay, thank you. It's a pleasure to be here. Good morning and good evening. And I'll be talking about random processes of graphs and permutations. And this combines extremal and probabilistic combinatorics. And hopefully it will be interesting. Part of it is a survey and part will be very recent. So let me start with a random graph process that probably most of you know. So that was due to Erdos and Renyi, and it's introduced in the first page of their paper on the evolution of random graphs, and also in the first page of their paper on the evolution of random graphs. And this is not a typo. They have two papers with the same title. One is a short version, one is an old version. And the process is the following. We start with the edgeless graph on n-labeled vertices. We take a random order of all the n choose 2 potential edges on n-labeled vertices, and then we just add the edges one by one. We denote by G sub m the random graph on n with the first m edges. And the good thing about it is that this process contains all the random graphs GNM, right? So this appears after we add the M edges. And maybe the nicest results here are stopping time results. And here I mentioned two classical ones. The first one is due to Erdos and Renyi. What they showed is that with high probability, namely with probabilities that tends to 1, as the parameters of the problem grow to infinity, the first value of m for which the graph GM has minimum degree 1 is exactly the first value of m where the graph becomes connected. And a similar, somewhat more complicated result proved independently by Bolobash and by Aitakov and Semrady is that with high probability, exactly the first m for which the random graph has minimum degree 2 is the first m where it becomes a Hamiltonian. Okay, so here is another random graph process, which maybe is somewhat less known or less studied, and I think it's also interesting. So I considered it a few years ago. It was also considered in a paper by Ferber, Montilegre, and Wu, and possibly also by others, because it's a natural process. So, so this is what I call the vertex random graph process. We fix some p in 0, 1, and then the p vertex random graph process, now it's an infinite sequence of graphs, G1, G2, G3, and so on, where Gi has I vertices. So we start with a single vertex. And when we want to generate Gi plus 1, from Gi, we just add one new vertex and we join it to each of the previous vertices randomly and independently with probability p. So this is again a nested sequence of random graphs, and Gn is of course exactly the binomial random graph Gn p. I should say, by the way, that like Jeff, I'm not trying to follow the chat. So if you want to ask something, don't hesitate to unmute yourself and ask a question or make a comment. So in this paper by Ferber, Montilegre, and Wu, this is used to study some random graph analogs of the law of the iterated logarithm. My motivation was investigation of k-induced universal graphs let me tell you a little bit about that. So we call a graph K universal if it contains a copy of every graph on K vertices as an induced subgraph. And this type of question was first considered by Rado and then by Moon and Vizing in the 60s. And a natural question here for the random setting is what is the smallest n, which is a function of k, so that the random graph Gn 1/2 is k universal with high probability. So just consider the usual random graph, every edge with probability 1/2, and we want to know for which values of n it will contain every subgraph on k vertices as an induced subgraph. So Bolbosh and Thomason showed that this is between some constant k 2 to the k over 2 and k squared 2 to the k over 2. And the nice thing is that they are not using any large deviation inequalities. This is still in the 80s. So they just use a second moment. It's always impressive when you can use second moment to get that something holds with exponentially high probability or exponentially low probability of failure. This is, by the way, the case with the proof of Yehudayov that Jeff mentioned in his lecture. Then there was a subsequent paper by Brightwell and Kwayakawa. They already used some large deviation inequalities, and they show that n of k up to a constant factor behaves like k 2 to the k over 2. And what I showed is that in fact you can find the value of n of k exactly up to a low order additive error term, and this behaves like k over e 2 to the k minus 1 over 2, and I'll soon tell you where it comes from. And moreover, if you look at the half vertex random graph process, so we generate this random graph process starting with one vertex and adding vertices one by one, always connecting them to the previous ones with probability half, then the first value of n for which Gn contains a clique of size k and an independent set of size k is with high probabilities the first value of n for which Gn is k universal. Once it contains a clique and an independent set, it contains everything. And this, in fact, together with a Stein-Chen method, can give even some precise estimate for the probability. So if n is such that the expected number of k cliques, which is the expression you see here, n choose k 2 to the minus k choose 2, is lambda. So if the expected number of k cliques is lambda, and if this behaves like a Poisson distribution, then the probability that there is such a clique is 1 minus e to the minus lambda. And if you believe that the clique and the independent set are more or less independent, so this is what the two-dimensional Stein-Chen method enables you to do, then it can be shown that if the expected number of cliques is lambda, then the probability that the graph is k universal, which, as we said, is essentially the probability that it contains a clique and contains an independent set of size k, it is roughly 1 minus e to the minus lambda squared up to some low order term. Now, let me point out that it is quite natural to expect that the clique and the independent set of size k are the most difficult graphs on k vertices to achieve. So once we get them, it's natural to suspect that everything else would appear. And this is because these are the graphs that have the largest number of automorphisms, and therefore the expected number of their copies in the random graph is smaller than the expected number of any other graph on k vertices. On the other hand, there are many choices for the other vertices, so the two things compete with each other. And maybe it's not so surprising that you have to use some group theoretic tools, specifically some classical result of Bochert and others about permutation groups that are not doubly transitive to estimate the number of graphs with a small number of automorphisms, and this gives what's needed for the random case. Now, this random result is actually useful in studying the extremal problem. So what is the extremal problem here? This is the smallest possible, we want to investigate the smallest possible number of vertices, f of k, of a k universal graph, a graph that contains every graph on k vertices as an induced subgraph. So as I already mentioned, this was first considered by Moon already in the 60s, and he showed that f of k is at least 2 to the k minus 1 over 2. This follows by counting, and at most a constant k times 2 to the k over 2. This follows also from the random results that I told you, but he had some explicit construction, and there were several subsequent papers over the years, and a few years ago there was this paper by Alstrup, Kaplan, Thorup, and Zwick, and they showed that they determined f of k up to a constant factor, so it is at most 16 times 2 to the k over 2. This is what their bound gives, and what I could show is that, in fact, again, up to a lower order additive term, this f of k behaves like the lower bound, 2 to the k minus 1 over 2, which would be the bound if we basically have a graph that contains every induced subgraph exactly once or a smaller number of times. And the construction uses the random part to include all the asymmetric k-vertex graphs, where asymmetric is defined appropriately. We want that no big subgraph of it will have too many automorphisms. And then there would be a smaller explicit part that contains all the symmetric ones. And again, here there would be some application of some tools from group theory. So this was an example where the random and the extremal problems are kind of connected to each other. Let me move to the permutation process, and here there is a very natural model of generating a nested sequence of permutations, and this has been considered in many places. So we let x1, x2, and so on be an infinite sequence of IID uniform random variables in 0, 1. So we just generate independently random points, real points in 0, 1. And then for every n, the first n values define a random permutation of n elements in the natural way, according to the order between the elements x1 up to xn, which with probability 1 are all distinct. So this is called the random permutation process. And as is the case for graphs, one place in which it arises naturally is a study of k universal permutations. So let me tell you something about this. There are some interesting problems there that are still open. So we say that a permutation of n elements, so this is sigma, think about n as big and k as small. So sigma is a permutation of n, and tau is a permutation of k elements. And we say that sigma contains tau if there are k indices, I1 less than I2 and so on less than Ik, so that the order between the tau j's is exactly the order between the sigma ij's. And equivalently, so I'll soon have an example here, but equivalently, this means that the permutation matrix of sigma contains the permutation matrix of tau as a submatrix. And what you see below here is an example. So here is a permutation of 7 elements, 1, 3, 7, 2, 5, 6, 4, and it contains 1, 4, 3, 2, as you see here in red, because the first red element is the smallest, then the next red element is the largest among the 4, the third red element is next to largest among the 4, and the last is next smallest. So they behave like 1, 4, 3, 2. So this is a notion of containing a permutation, and we call a permutation of n elements k universal if it contains every permutation tau of length k. And again, the random question here is the natural question about the random setting is what is the smallest n, which is a function of k, so that if we take a random permutation of n elements with high probability, it will be k universal. So if we want to think about the random permutation process, what is the smallest n so that the nth permutation in the random permutation process is typically k universal. And one thing to observe is by the known results about the longest increasing subsequence. So there are very detailed results about the longest increasing subsequence, about the distribution, about this Tracy-Widom distribution, the Irie function. So they started with Logan and Shep and Vershik and Kirov, and then the main result or the breakthrough was by Bike, Deift, and Johansson. So we know that the longest increasing subsequence with high probability in a permutation of length n is roughly of size 2 square root n, and that says that the length of n of k in order for it to contain an increasing sequence of length k should be at least something like k squared over 4. So this would be a lower bound. And then the question is, what is the truth? So this is a conjecture I suggested quite some time ago. And the strong version of the conjecture is that this n of k is indeed 1 plus theta 1 k squared over 4. So what is enough to get an increasing and a decreasing subpermutation of length k is enough to get everything. Here I would hesitate to conjecture a stopping time result, because you see, unlike the graph case, here's the expected number of copies of any permutation is exactly the same. It's always n choose k divided by k factorial, and only the variances varies. So it's not like in the graph case. A weaker version of the conjecture is that this n of k is constant k squared. And an easy thing to prove, you can try to think about it, is that n of k is at most some constant k squared log k. And 2 years ago, Xiaoyu and Metwan showed that n of k is at most k squared log k. So still, even the weak version of the conjecture is not known. And it would be interesting to prove it. Again, here people consider the extremal problem as well. So here we can denote by g of k the smallest possible length of a k universal permutation. And by counting, this g of k is at least roughly k squared over e squared. So this is just by counting. And Arakia conjectures that this is tight, but this conjecture is incorrect. So it was disproved recently by Kroman, Kwan, and Singal. And they thought g of k is at least a little bit bigger than that. So it is 1 plus c times this counting lower bound, where c is some fixed small absolute constant. What about the upper bound? Well, the upper bound, maybe the upper bound that is known is what is written here, roughly 15 over 32 k squared. So this was announced by Zach Hunter, but I still haven't seen a paper. There are several papers that prove an upper bound of roughly half k squared. And if this stronger upper bound is true, then it refutes a conjecture by Eriksson, Linson, and Wastlund that the truth is roughly half k squared. But even if this, as I said, is not published yet, so still note that this conjecture, even if we don't know it to be false, it definitely contradicts the strong version of the conjecture about the random permutations. It says that k squared over 4 contains already everything. So there are quite a few questions and conjecture there. Certainly, some of them are false, and in fact, it's possible that all of them are false, but there are some interesting questions. Okay. Now, the second half of the lecture is about a very recent result, and it still deals with a random permutation model. And this is on a random model of forgetting, and it's a joint work with Dor Elboim and Ellen Sly from Princeton. And let me tell you the question. So again, if you lost me, I'm starting now something new, so you can start to catch up again. So here is a process. It was suggested by Georgiou, Katkov, and Tsodyks. We have again this x1, x2 up to xn IID uniform in 0, 1. And we start with S, which I'll call the memory for reasons that maybe I'll explain at the end. So S at the beginning just contains only 0. And then the numbers xi enter S one by one in order. Whenever a number that enters is larger than the minimum of S, then the minimum leaves. And if it is the minimum, the new element, then it stays and the size of S increases by 1. So here is a simple example. x1 up to x6 are 0.7, 0.8, 0.2, 0.9, 0.5, 0.6. They enter in order. So you see, at the beginning we had 0, then 0.7 came, it is larger, so it enters, 0 leaves. Then 0.8 comes, it is larger than 0.7, so 0.7 leaves and 0.8 stays. Then 0.2 comes, it is smaller, so it enters the memory and the size of it increases by 1, it's 0.2, 0.8. Then 0.9 enters, throws 0.2, 0.5 enters, it is smallest, so the memory increases by 1, and when 0.6 enters, then 0.5 leaves. And the motivation that, as I said, I'll mention at the end, is a possible model of forgetting. And these guys are neuroscientists, although they all came from physics by education. And the problem was to analyze this process. What is the typical final size of S? What is its distribution? And they simulated it. And the simulation suggests that the typical size of S after n steps is close to n over e with high probability. And indeed, the first proposition that we proved, and I'll try to tell you something about it, is that indeed, with high probability, the size of S after n steps is up to low order additive error term n over e. And moreover, essentially what happens is that at the end, after n numbers, random numbers between 0 and 1 enter, essentially almost all the ones that are bigger than 1 minus 1 over e stay, and almost all the ones that are smaller than 1 minus 1 over e leave. So the picture looks like the ones that you see here, right? Almost all the big elements stay, almost all the small elements leave. And I wrote here that Friedwood and Kozma also analyzed a similar infinite process and proved something similar without the quantitative estimates, but basically similar. But we know much more, so let me tell you some more detailed information. So here is the first theorem with your Elboim and Allan's slide. Let me denote by S1n, so that's just a notation. This is the content of the memory S after n steps. Then as n tends to infinity, if we look at the size of S1 t times n, so think about t as any number between 0 and 1 now. So after tn steps, we said that the typical size of the memory is Tn over E. So let's subtract Tn over E and divide by square root n. Then it turns out that this converges to a standard Brownian motion with a variance 3 minus e to the 1/2 over E. So this is what you see here. And you see it in particular, it tells you that the size of S1n at the end, it converges to a normal random variable with expectation n over E and variance 3 minus e n over E squared. But of course, it says much more. It says also that what happens up to time Tn and what happens between time Tn and time T prime n is kind of independent. Namely, it really behaves like a random walk with some tiny steps. Here is a simulation, actually. So this simulation of what happened. Question? Yeah, I'm not there. Okay. Yeah, as I said, don't hesitate to stop.
It
does not sound like a question. Okay, so here is a simulation. We did it. It's of course something that is very easy to simulate. So you take a million random uniform numbers between 0 and 1. What you see here is, as a function of k, you take the size of the memory, subtract k over e, and this is the deviation. You see that it really looks like a Brownian motion or random walk. The standard deviation is close to 200 here, and this is how it looks. Now we actually know also about the behavior of this memory. I told you that basically most of the elements above 1 minus 1 over E stay, and almost all the elements below 1 minus 1 over E leave. Here is a more formal statement. So let's denote by Z naught 1 minus 1 over E. And let L for left, Ln will be the content of the memory minus all the elements that came that were bigger than this 1 minus 1 over E. Okay, namely, how many elements that are bigger than 1 minus 1 over E did not stay in the memory. Actually, maybe sorry, I guess I wanted to write here, maybe I wanted to write the inverse of this, but maybe the difference, all the elements that are, let me state it again. Ln is for left. So this is the content of the memory at the end, which are elements smaller than 1 minus 1 over E, right? We throw all the, how many elements smaller than 1 minus 1 over E stay, and the right is the number of elements that are bigger than 1 minus 1 over E that left the memory, that did not stay, okay? And then here is a second theorem. So if we look at this pair of random variables, this left elements scaled divided by square root n, and the right elements divided by square root n, then this pair converges to one of them converges to the maximum of the Brownian motion, and the other to the maximum minus the Brownian motion itself. And again, we will see, I'll show you soon a result of simulation, but in particular, that means that both this ln over square root n and Rn over square root n converge to up to some scale to an absolute value of a normal distribution. Here is how it looks. We just have here two runs of this LK in blue. So these are the small elements that stay in the memory at every given time step. And the red is the elements that are bigger than 1 minus 1 over E and do not stay. And you see here two runs for K equals 100. So you see that what happens is that basically one of them, namely the red thing, this is the elements, the number of elements that are bigger than 1 minus 1 over E and left. Of course, this keeps increasing, right? So the numbers, elements that left already, so this can only increase. So this behaves like the maximum of a random walk with tiny steps or Brownian motion. And you see that this stays constant for a while, and then whenever the random walk approaches a maximum, and therefore the difference between the walk and the value of the maximum is 0, so in the blue, you see that we hit 0, then the maximum can increase again. And then maybe it stays put for a while. And then when the blue hits 0, it increases again, and so on. And you see that this is a similar thing happens for the random process that we are considering, right? So as long as the minimum is less than 1 minus 1 over E, then the elements that leave will be less than 1 minus 1 over E, and therefore the red thing will not increase. And from time to time, the minimum becomes bigger than 1 minus 1 over E, and then the number of elements that are bigger than 1 minus 1 over E that leaves can increase. Okay, so this is how I want to tell you something just in a few minutes, just a sketch of the proof of the very basic result that the size of the memory at the end behaves like n over E, and I just want to show you where this 1 over E or 1 minus 1 over E comes from. So let me denote by S of Z and M. This is a number of elements xi that are at most Z that lie in S after the first M steps. So Z will be some number between 0 and 1, and M could be any integer. This is some notation. And then one can prove the following three lemmas. And the first one is that indeed the memory increases linearly. Namely, the expected value of the number of elements in this memory S after M steps is bigger than M over 4. We said that eventually it will behave like M over E, but there is a very short proof that it's bigger than M over 4, so it grows linearly. Another fact is that for every fixed C, this expected value is sub-additive in M. namely, whenever we look at the value in M1 plus M2, then it is at most a value in M1 plus a value in of M2. And because of this, by Feketter's lemma, the limit of this expectation divided by M exists. Okay. And lemma 3 is that with high probability for every fixed Z, SZM is concentrated around its expectation. It is within little of M of its expectation. And I just wrote here that all these lemmas are proved by combining combinatorial arguments with the Azuma-Hofding-Martingale inequality applied to the natural Doob-Martingale. So there is some nice combinatorial argument here, but basically this is not difficult. So these are 3 lemmas. And now we can fix some small epsilon. And we choose Z naught, so we still don't know at the moment what Z naught will be. So this Z naught will be some number between 0 and 1, so that the limit of the size of the memory, of the number of elements in the memory that are smaller than Z naught in the first 10 steps divided by M, if we look at the expectation, this is epsilon. So this exists by lemmas 1 and 2, because the first lemma tells us that this grows linearly, and the second lemma tells us that the limit exists, and it's not difficult to see that it is continuous, so you can find ones that where it is epsilon. And then because of the concentration, this was lemma 3, with high probability during the process, after M steps, we have roughly epsilon M elements smaller than Z naught, right? Because we expect to have their epsilon M, so we have very close to epsilon M. And if we have epsilon M, then it means that the minimum will be below Z naught. So the minimum removed will be smaller than Z naught. And moreover, at the end, very few elements smaller than Z naught remain in S, because only epsilon N of them will be there. This is how we define it. So it means that basically this shows that at the end, what we have for S is roughly all the xi which exceed Z naught, and only those, all the ones that are below Z naught, they all left, right? Or almost all. So now suppose for simplicity that indeed at the end, S contains exactly all xi exceeding Z naught and no other xj. I want to show where the 1 over E comes from. So what I wrote here is that if some xi is x, the number of not necessarily consecutive, actually necessarily not consecutive time steps in which xi is the minimum, you see it can be the minimum, then someone smaller comes, and then it's not the minimum, but later this guy leaves and it can be the minimum again. So the number of times it is the minimum until it leaves is a geometric random variable, and its expectation is 1 over 1 minus x. We just wait until someone smaller comes. And the expected number of xi between x and x plus dx is n times dx. And therefore, since an element between x and x plus dx stays 1 over 1 minus x steps, and we have n dx of them, then the integral from 0 to Z naught of n dx over 1 minus x is n, because these are all the n steps. And then we just solve this integral, and this gives that Z naught is 1 minus 1 over E. And so something was hand waving, but this is basically it. Let me just mention that the more sophisticated theorems are proved by defining and analyzing a more sophisticated martingale, which we call the branching martingale, and by applying some central limit theorems for martingales. And there is some intuition behind this definition, which is multi-type branching processes. I'll not talk about this. This is a process here in which the number of types is infinite. And just something about the random model of this Georgiou, Katkov, and Tsodyks. So then think about the numbers xi as pieces of memory. And larger xi correspond to a more important piece of memory than a smaller one. And now the memory is limited, and hence when a new item arrives, then the least important piece is being forgotten, unless the new arriving item is really the smallest, and then it stays always for at least one step. Now, something disappointing a little bit is that experiments, so there are ways to do experiments with people in Amazon, actually, and they did it. So you ask them to remember words and check it, and they kind of suggest that that really this model does not quite work as it is. Still, I think that mathematically it is intriguing, and note that one point in it is that in this model, you always remember the last final item, because the final item always stays. And this is the last piece of this lecture, so you are supposed to remember this one. And with this, I'll finish, and thank you.
Any questions, feel free to unmute yourself. So maybe I will start with a non-technical question. Noga, do you think it's, for the last, this forgetting model, do you think it's interesting to consider some sort of two-dimensional analog you have in the square?
That's right.
0, 1?
You mean for this forgetting process?
Right.
Right. Yeah. So it's a very good question, because actually they consider this model as well, and they change it a little bit, namely, and they do it in any dimension. So points come in 0, 1 raised to the power k, and there, whenever an element appears, then all the ones that are smaller than it in all coordinates leave. So for k equals 1, this is something that is called records and is very well understood. For higher k, one can analyze it and get some results. And actually, if you believe this experiment, someone looks at the behavior of memory of people corresponds to the 7-dimensional model of it. If we deal with words, and if we deal with small pictures, then it corresponds to a 5-dimensional version. So there are also some interesting questions about this high-dimensional model, but this is just to say that it's a good question, and it has been considered, at least in some version.
Thank you.
Mm-hmm. So maybe I can stop sharing, and so that I see some of you, right? Yeah. Okay. Right. Yeah. Mm-hmm. Okay.
Hello. Nice.
Yeah. Right.
It's a new random graph model, right? You consider it the first time, and I'm not. You can understand what I say?
I'm not sure I understood. Can you repeat it? So in the random graph model?
It is the first time you discuss the random graph model, define this random graph model, right?
You mean this vertex random graph process?
Yeah.
Right, yeah.
And you give very beautiful results. You relate them with the Brown motion, BM motion, and some continuous process. but you only give some distribution results. I'm curious, have you considered some heating time? Because you, at the beginning of your speech, you give some results about the, you know what I say? I'm sorry.
Yeah, okay. So there are two unrelated things here. So one of them is a model for the graphs, the vertex random graph model. And the other is one about the permutation model. And this one, this question was related to this Brownian motion.
Yeah.
So something converges to a Brownian motion. I mean, so I'm not completely sure what will be a heating time question for this model, but maybe there could be one could formulate some heating time questions for the permutation model, but maybe not for this model of forgetting. I mean, for the other questions I mentioned, there were these heating time questions of maybe when a permutation becomes K universal, and that could have an interesting heating time result, which I said I'm hesitating to conjecture, but it's not impossible that it's true that once a random permutation contains an increasing and decreasing subsequence of length K, then it always already contains with high probability everything. So this is possible, but I'm not sure if I would conjecture it, because it behaves a little bit differently than the random graph. So I hope this is some sort of answer to the question.
Okay. Could you change your model to some graph process? Okay, you related permute. Yeah, the problem can change to some graph process you discussed before. Sorry.
Okay, so there are so there are here both graph processes and permutation processes, and both are interesting, but I think they are meant to be shown just as two examples of random processes, just as a Brownian motion is a third example, well, probably the most studied example of a random process, and as we see, well, there is at least a connection between the some question for the permutation model and the Brownian motion model, but for the graph process and the permutation process, I don't see any direct connection.
Thank you. It's very interesting. It's a big application. So I'm interested in this model. Maybe my question is not right. Thank you. Thank you for your answer.
Okay. Thank you. Thanks. Mm-hmm. Thank you.
So any other questions?
We have this theorem for universal graph and universal permutations. Are there other results, like maybe post-sets or uniform hypergraphs or some other discrete structures?
Right. So it's very natural to define this random vertex random graph process for hypergraphs as well. And I guess the same questions can be asked. People looked at universal hypergraphs, and there are some results, at least for the extremal questions, that are similar to the graph case. At least the results that I know do not reveal any really new phenomena, but sure, these random processes can be considered as well. So yeah, so it's also a good question. I was told once that when you don't have a good answer, you should always compliment one who asks the question and say that it's a very good question. But it is a very good question. Okay. I see.
Noga, there's a delightful cartoon of Ra's chests that shows this model of memory at work. I put a link in the chat.
Okay, I should look at it. So
At your leisure.
okay, and you said that it's in the chat now, or what?
I put a link in the chat. Yeah, a long link.
Okay, I'll look. Right. I mean, I'm always, yeah, I see it, but I always worry that once the lecture is over, then I lose the information in the chat. So maybe, but I'll send you an email and ask you to send it.
Happy to do that.
Okay, thanks.
So if there's no further questions, let's thank Noga again for the very nice talk.
Engineering of CSS.